am recording. Hello, I'm Gabrielle Taylor. I'm going to be doing homework 1 part C. So let me share my screen. Okay, so homework 1 part C says, while implementing a Python code, attain the Anton coefficients of water by a nonlinear regression of the vapor pressure data. Okay, so first, let's import NumPy as MP. And then we are going to want to do plots. So from SciPy dot, and what we want to do is we want to graph our data, and then we want to minimize our sum squared error to find a line of best fit. So we need to find optimize. So we need from optimize, we need to import minimize. Need minimize. Okay. Next, for our plots, we need from plot ly dot make subplots. We're going to import. No, sorry, it's plot ly, and then this one's going to be just subplot. So we're going to import subplots. Make underscore subplots. Okay, so let's see if these work. See if I spelled everything right. I think I spelled minimize wrong. Okay, so after we get our imports in, then we are going to want to take our data. So I'm just going to take data from the web. So we get, and then I have the raw data here. So I'm just going to do the URL, just copy and paste it into here. And then, okay, so it was approved. And now what I want to do is, now that we have the data, I want to assign it to what it is. So pvap data. And this is going to equal our, we want to MP load text. So we want to load the text that it's in. And then what we want to do is we want to name our file that it's at, which that's water pressure. And there should be vapor in there. Vapor, pressure, and then this is a CSV file. And then what we want to do is just separate between our commas so that they know what it is. And then we need a comma in here. So this just separates the commas and makes it two just separate things. Okay. See if that runs. Okay, so that runs. And now since we have two separate things, I want to assign them our X's and Y's. What our X and Y's on this is going to be our temperature and our pressure. So our first one is going to be T, and the next one is going to be pressure at the equilibrium curve. And then we want to make this equal to the pvap data. And this is going to be dot T because this is going to be a respect to T. Okay, so that loaded. So now that we have our T and our pressure experimental, now what we want to have is, we want our model. So that's going to be the Anton's equation, and we want to subtract it from our pressure experimental to find our sum squared error. And then after that, we want to minimize our error so that it fits the line best curve on the nonlinear regression. So what we're going to want to do is just make, let's define a function. and I'm just going to say Anton. I'm going to say V for now because Anton's equation is going to be A, B, and C because we want to find our variables. We want to find A, B, and C, and we want to make that equal to V. So what we want to do is our model is going to equal Anton's equation. So 10 to the A minus B divided by T plus C. T plus C. Okay. So this is Anton's equation. And now what I want it to be returned, we want to return our sum squared error. So MP dot sum. So this is a sum. And then what we want to do is we want to subtract our model from our pressure experimental. And then we want to take that and we want to square it. It doesn't matter which way you do. You can do pressure minus the model. It doesn't matter because we're squaring it. So let's see if this works. It does. So let's move on to the next thing. Okay, so now that we have our sum squared error, we want to minimize it. So let's do Anton, and then what we're minimizing is our A, B, and C. So I'm going to say A, B, C. And this, since we imported the function minimize, you can just do minimize. And then it wants to know what function we have. So we put the function first. So this is just Anton. And then what we want to do is we want to make guesses, our best guesses of what it's going to be. So this is what I found works for me. So I did 10.21, 2000 dot, and then I think it's like negative 36, I think works well for this one. And if it doesn't, I can try different ones. Okay, and then we multiply it by x. So, okay, it works. So now what we want to do, so we have our minimize, we have our Anton's equation. Now we want to do our final Anton's equation. And this one is just going to be our it's going to be our Anton's equation. And then when we graph it, we're going to put inside these minimized A, B, and C that we found. So let me just see what values we came up with in A, B, and C. Okay, these are good. And then let's go and try this one. Okay, so let's do final. Let's define final Anton equation. So defined final Anton. That should be good. Okay. Oh, and this is going to be also in respect of V, which is V is going to be our A, B, and C. B, C equals V. And I think it's just going to return. So then we just wanted to return our pressure. So we're going to find A, B, and C, and then when we graph it, we'll give it temperature. So then we just need our pressure. So pressure is going to equal this. So we just got to find pressure. So D plus C. Okay. Next, what we're going to want to do is now that we have everything, we can graph it. So let's do figure equals make underscore subplots. And then what we want to make is we want to make we want to graph our points that we got from our experimental data. So figure, and then make scatter. No, I think it's add scatter plot. I think it's add dot add underscore scatter. And then our x is going to be our temperature. Our y is going to equal our pressure, experimental, and then our markers. So I think it's mode equals, let's say markers. And this should be good. And then the next one is going to be figure dot add scatter as well. And this one's going to be x is also going to be our temperature. Now this, for y, we want to do is our final Anton's equation. Final Anton right here. And then inside it, we want to have our A, B, and C that we minimized. Anton, A, B, C. Okay, next, our mode should be lines. Lines. And then this is going to be at a logarithmic scale. So what we want to do is we want to do our figure, and then we want to update our plot. I think it's dot update y-axis, please. Update underscore y-axis. And then we want to make it, I think it's log. I think it's log. Let's run this. The function, oh, I think the function work. Okay, so this is our graph that we found. And so what it's pretty much doing is we are trying to find the error from our line to our points. And what we're doing is trying to find the line best fit. So in the beginning, you can see that the line and the points are really far apart. That is okay, and that's going to make our error less just because our points up here are extremely close. And at the points up top, we're at the 2 million mark, or at the 12 million mark. So our error up at the top when you're going in 2 million is really close. So that's going to keep our error down. And when we're in the 5K to like 2K region, we're going to be off a little bit, but that's not comparable to 12 million and being off in the millions. So this is a good line best fit, especially because the higher pressures are going to be able to match. And they're matched up pretty well for above millions and the higher temperatures and pressures. So this is good. So now the next part of homework 2 is we want to derive a linearization form in the Anton's equation, and we want to do this with a design matrix. So let me unshare my screen. Okay, and let me use my board. Okay, so the first thing is the Anton's equation is going to be log base 10 of pxp, and this is going to equal a minus b over t plus c. Okay, so for our design matrix, we want our y and we want our coefficients. So we want a, b, and c all by itself. And so we can make this into our own design matrix. So the first thing that we want to do is, this is going to be really hard if we have anything underneath, or if we have anything on the denominator. So let's multiply everything by this so we can get this out of the denominator. So on this side, this is going to be t plus c log base 10 of pxp. And then on this side, it's going to be a times t plus c minus b. Okay, so what we want to do is, now that we have everything by itself and we have our variables a, b, and c, let's multiply everything out and then let's separate our variables according to the matrix. So first, let's do t log base 10 of pxp, and then we have plus c log base 10 of pxp. And then this is going to be a t plus ac minus b. Okay, So on this side, we have T log base 10 of pressure. This is really good because this is going to be our Y because there's no variables in it. This is what we're going to use. So we want to get this by itself, and we want to put all the variables on the other side. So let's put all the variables on the other side of this. Okay, so what we want to do for our design matrix is, let me make this a better scene. Okay, what we want to do for our design matrix is we want to make that our variables, we want them to be separated equally by itself. We want each variable to have one thing by itself. We don't want two. So let's do the first column in our design matrix. Let's just do AT. Okay, so we have AT, so we have a row of T's. So this is T1, T2, and I'm just going to do dot dot, and this is going to go to Tn. Okay, so then our next coefficient that's all by itself is, let's do C, because it's going to be easier if we do C. So our next one is going to be negative log base 10 of P. Negative log base 10, and this is 1, negative log base 10 of P2, and then dot dot dot, this is going to be negative log base 10 of Pn. Okay, so now what we have left is we have AC, which is not really going to help us out because this is two variables multiplied by each other, and then we have B, and we only have one space really left for it because we only have 3 variables. So what we want to do is we're going to make this our own separate variable, and we're going to just solve for it later. So let's make over here, let's make this AC minus B equals D. Let's just make this D. And so D would only have 1 in front. So we just have 1, so all of these are just going to be 1. And that's going to go for n many amount of terms. So next is our variables. So we're going to multiply this by this. Well, these two are going to multiply. And this is going to be A at the top. And the next one is going to be C, because we have it here. And our next one in our one column is going to be D. Okay. So now we have our Y's. Our Y's. Well, let's think about this so we know the shape of our Y. So this is n, because this goes for n amount of terms, and then the columns are 3. So this is n times 3, and then this is going to be 3 over 1, so 3x1. So when these multiply, it should be n amount of terms on the rows, and then there should only have one column. So let's write that down. So we have T log base 10 of P. P. This is 1 log base 10. And this is dot 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 log base 10 of P xp. And this is n. Okay. So how to solve this is we want to get this to be over here. We want to multiply this by its transpose. When we multiply it by its transpose, it's going to be a 3 by 3 matrix, and I'll show you how that works. Okay, so a transpose is pretty much just flipping this and turning it over. So over here, so the T's are going to be at the top. This is 1, 2, and then this is going to be your negative log, and negative log. And there's pressure inside of it. I'm just doing a quick thing to explain it. That's to the end, and this is just 1, 1, 1. Okay. So if we look at this and we look at the design of it, it's going to be 3, the makeup of it. It's going to be 3 because there's 3 rows and it goes on for n amount of rows. So 3n. So 3x. So when we multiply these together, what you're going to get But you're going to get a 3 here because we do the first one, we do the rows, and then when we multiply it, we do the columns. So it's going to give us a 3 times our 3x. So this is going to give us a 3 by 3 matrix. And that's going to be easy for us to solve. And when we multiply a transpose, the matrix we're going to get, it's going to be this. It's going to be 1, 0, 0, 0, 1, 0, and then 0, 0, 1. So when we multiply it, so we multiply this top row here, go top, then we do our A. This is going to just give us A. And then when we multiply the second, it's going to give us C. And then when we multiply the last one, it's going to give us D. So inherently, this is just going to be A, B, C, A, C, D. And so when we go over here, because if we multiply this side by our transpose, we have to multiply that side by our transpose. So when we multiply this side by our transpose, I'm just going to say A dot T. What's going to happen is this is a n to 1, and this is a 3 to n. You multiply these together, that's going to be the A transpose, and then it's going to be our y here. So this is going to give us a 3 to 1 matrix, and so it's going to give us A, C, and D. And those are going to give us our variables. And then when we get our variables, we'll get D. And we'll plug it into this equation here, and then we'll be able to get our B. So then we'll have our coefficients. So let's code it. So let me pull up our previous code. Okay, so the first thing we want to do is we want to make our A. I want to make our A matrix. So our A matrix can be A underscore C. This is just going to compact our data. It's going to compact our arrays together, and it's going to make us our matrix. So what we do is now we put our T, because we already have our T from our previous data here, like so, T. And then actually I'm going to do something to make my life a little easier. I'm going to make log PXP, and then so log of PXP, and then I'm just going to do log, I'm going to do np dot log base 10 of, oh no, of that. Okay. So now for our second data, it's going to be the negative log PXP. Okay, and then our second one is going to be np dot ones like RT. This means it's just going to repeat 1 all the way down, because the code doesn't understand that the 1 is going to repeat itself. And then it's going to keep us in the same format as our T, which is going to be a float, which is going to help us multiply. So it should be good. Oh, I think it's this actually. There you go. Okay, so let's look to see what it looks like first. So it copied down the 1s, it gave us this, and it gave us our temperatures. Pretty good. So after we have our 1s, what we're going to want to do is we're going to multiply both sides by our A transpose. So what we got to do is just, we're going to do is NP, linear algebra, linear algebra, linear algebra dot solve. That's solve. And then the first thing we're going to do is we're going to do A times T. And then when you multiply two matrices, it's going to be the add symbol. I need to actually capitalize that T, then the add symbol, and then just our matrix that we made. And then our second one is it's separated by a comma. And now we're going to do our y side, which our y was a dot t times a dot t. Oopsie, okay. Multiplied by our t times our log base 10. Log, sure. Okay. And what this is going to give us, like I showed you on the board behind me, is this is going to give us our A, C, and D. And should be in that order, so I'm going to make this variable equal A, C, B. Okay. My next one should be, so after we found our A, C, and D, let's just see what it looks like. A, C, D. This is good. Okay. So now our next one should be, since we have our D, let's just solve for, and let's get our B, because that's what we want. So B equals, and then if we look on the board, we had AC minus B. So we just need D minus, what should be D plus A times B. Okay. And now we just compact these together, ACB for our Anton equation, and then we found our coefficients doing the design matrix.